this assignment, the RLC Uncovering Relationships competency assignment. And initially, we started with an RLC circuit that was sourceless. In other words, there was no, after we used a battery to set up the initial conditions, there was no source in the circuit to deal with. And we additionally examined the case where the resistor is absent, and then the third thing we looked at, the third circuit we looked at, was this one. Comprising, again, a series circuit with an inductor, a capacitor, and a resistor, and a variable power source supplying 5 volts sinusoidally. An alternating source. The potential across the source alternating between +5 and -5. And we observe the response. And we also observed the phases of the responses. Let me get us into stable condition here. We note that at any given time, 1.37 seconds, the potential difference across the capacitor and the inductor are out of phase, 180 degrees. At the same instant, the capacitor voltage has a minimum, a negative maximum, I suppose. But as far as the sinusoidal function is concerned, a minimum. The inductor voltage has a maximum, and vice versa. But that the resistor voltage has a 0 there, or at least something very close to a 0 there. And that at 1.37 seconds, it appears that the source also has a maximum, which I guess is interesting enough, but also the current response what does this curve represent? Because these three graphs all have current maxima at the same time. And it makes sense that they should. They are all in series, but aren't they in series with the voltage source as well? So shouldn't the current passing through the circuit be the same everywhere? What is this? What is this? And how does it relate to the potential difference across the source? Why are these two things out of phase? But how are these graphs sensible? How can we make sense of these graphs? That's our goal today. How does the fact that there is an alternating source affect the results that we obtain from our differential equation? Why are we interested in using an alternating source in the first place? What would be the advantage of this over this?
The alternating current doesn't damp.
Okay, so in this circuit, the response is attenuated by that exponential deal that we talked about. And if we supply power to match the extent to which the energy of the system would be decreased by dissipation across the resistor, we can preserve the oscillation. We can maintain behavior. Okay. We could think of the resistor as a task that needs to be performed. We could think of the resistor as a load, some job to do. And if that electrical job that we need to perform is consistent, I'd like to make sure that the sort of power that we deliver to that load is the same. If we allow the power dissipated in the resistor to decrease, as it looks like it's going to without a source, then we aren't doing a consistent job. And eventually this thing is going to stop running, whatever this is. If it requires current passing through it to do a thing, like, I don't know, rotating the bit of a drill, for example, then this is not a great application. We do want to supply, and in fact, when we connect the corded drill to the wall, we do supply continuous power at exactly the rate that it would be dissipated by the load. Okay. I think the other reason we might be incentivized, sort of a similar reason, a a recreational turn on a swing set is a good deal less fun if there's nobody pushing you, especially if you're, a kid, and you're maybe not as able to like get yourself going the way we kind of learn to. Someone needs to give you a push. One push, though, isn't going to do it. I mean, it'll be nice for a minute, but then you'll, swing back and it'll be over. I mean, the resistance and the inertia of the chains of the swing or the rope or whatever will attenuate your energy and you'll end up stopping really quickly. So we'd like to push again. And there is a natural frequency with which a pendulum, simple or physical, in other words, with mass distributed throughout the system, instead of just at the end in the pendulum bob, there is a natural frequency with which this system wants to oscillate, even though there is some energy loss to friction in the chains and the inertia of, it's et cetera, et cetera. Air resistance, I suppose. There is a natural frequency with which that system wants to isolate or oscillate, excuse me. And that's the frequency at which we should apply our driving force, our push, to achieve maximum swing response. So we can get the largest load delivered for the smallest input power if we have a source with the right frequency. Two reasons. Maximum response is possible, and we can preserve the response. We get a consistent oscillation as opposed to one that dies out. Okay, cool. So I think, given all this, that we are, I think, incentivized to use an oscillating driver, an oscillating source of EMF in our RLC circuit to maintain the largest power input to output ratio that we can. Now, that's a little bit of a strange thing to say, isn't it? How would it be otherwise that the input power and the output power are different? That's energy conservation. That's the whole thing. That's Kirchhoff's loop rule. How would they be otherwise? And I guess what we mean is that the choice of driving frequency and the fact that we're using a sinusoidal source means that we can adjust, on average, the response. So of the largest possible response we could get from our input, we're trying to get as close to that as we can. Otherwise, the system doesn't respond the same way we are driving. Like we're trying to get the system to do something other than it really wants to do. And some of our effort is going to sort of enforcing that response from the circuit as opposed to its natural response. In other words, you could make a swing oscillate with other than its natural frequency, but you would have to grab a hold of the chains and move it yourself. You could enforce an oscillation of not the natural frequency, but it would be a huge waste of your effort because you, at a certain point, you would be working against the natural motion of the system. You would push it a little bit, like if you tried to make it oscillate faster, you'd push and it would naturally try to go forward and you'd be dragging it back, and that would be misspent energy in a certain sense if what you wanted was, maximal use out of the power that you were exerting. All right.